In this lecture, we will encounter and derive some trigonometric identities, including the compound angle and double angle formulae, and the auxiliary angle formula. We will also look at an example question that uses a real-life model involving trigonometric functions. An identity is a statement that holds true for all possible pronumeral values. We have already encountered some trigonometric identities, including the fact that tan theta equals sine theta on cos theta, and the reciprocal of this identity. We have also seen via the unit circle coordinate definition for the trigonometric functions that the square of cos theta plus the square of sine theta equals 1. Similar results to this can be found by dividing the identity through by the square of cos theta. The result is that 1 plus tan squared theta equals sec squared theta. In the same way, dividing through instead by the square of sine theta gives the result that cot squared theta plus 1 is cosec squared theta. Another set of identities are known as the compound angle formulae. The compound angle formula for sine of a plus b expresses it in terms of trigonometric functions of the angles a and b alone. We have that sine of a plus b equals sine of a times cos of b plus cos of a times sine of b. Let's derive this identity with the help of a simple diagram. Here we have a generic triangle ABC with the altitude from A meeting BC at D, and splitting angle A into angles alpha and beta. The triangle area formula tells us that ABC's area is half BC times sine of alpha plus beta. It also tells us that ABD's area is half HC sine alpha. We can replace H here with B cos beta, as seen in triangle ADC. In the same way, we have that ADC's area is half HB sine beta. This time H can be replaced with C cos alpha, as seen in triangle ABD. Putting these together, we know that the area of the original triangle is the sum of the areas of the two smaller triangles, which can be expressed algebraically like this. Cancelling this through by the non-zero half BC gives us the compound angle formula that we wanted. Other compound angle formulae can be derived similarly. Here we have listed all 6 standard compound angle formulae. These identities should be memorized for use in certain kinds of questions. The double angle formulae are special cases of the compound angle formulae. These are found by equating A and B in the general formulae. Doing so for sine tells us that sine of 2 theta equals 2 sine theta cos theta. Doing so for cosine tells us that cos of 2 theta is cos squared theta minus sine squared theta. And doing so for the tangent function tells us that tan of 2 theta equals 2 tan theta divided by 1 minus tan squared theta. Notice that the double angle formula for cosine can be rearranged with the help of the identity cos squared theta plus sine squared theta equals 1. We get the alternative results that cos of 2 theta equals 2 cos squared theta minus 1, and cos of 2 theta equals 1 minus 2 sine squared theta. The compound angle formulae can be used to find exact values of non-standard angles. For example, if asked to find the exact value of cos of 15 degrees, we can instead interpret this as cos of 45 degrees minus 30 degrees. Using the appropriate compound angle formula, we can find an expression in known exact values. Simplifying yields the result that cos of 15 degrees is the square root of 6 plus the square root of 2 all over 4. The trigonometric identities we have seen can also be used to prove new identities. For example, we could be asked to prove that tan of theta plus cot of theta equals sec of theta times cosec of theta. Usually, a good approach to these sorts of questions is to first convert all terms to new terms that only incorporate the functions sine and cosine. Here, we can rewrite tan as sine over cos, and cot as cos over sine. Adding the fractions results in a numerator of sine squared plus cos squared, which we know equals 1. It is now easy to convert the result into the expression on the right-hand side. The auxiliary angle formula allows us to convert a linear combination of the sine and cosine functions into an expression incorporating only the sine function. Consider the general expression a sine x plus b cos x, where a and b are constants. We would like to write this as simply r times sine of x plus alpha, where r and alpha are new constants. Expanding this out, we can rearrange terms and find that such a conversion can be made if a equals r cos alpha and b equals r sin alpha. We can combine these two conditions on a and b to find simpler conditions on r and alpha instead. First, note that a squared plus b squared has a factor of sine squared plus cos squared, which we know to be 1. This means that r squared equals a squared plus b squared. So if we take r to be positive, we have that r is the positive square root of a squared plus b squared. Also, notice that we have that cos of alpha equals a divided by r, while sine of alpha equals b divided by r. So we can directly find alpha in terms of a, b, and r. In particular, we need to solve for both the sine and cosine formulae so that the correct quadrant for alpha can be determined. To summarize the auxiliary angle formula statement, it is always possible to write a sine x plus b cos x in the form r sine x plus alpha, where r equals the square root of a squared plus b squared, and alpha is found from the two formulae cos of alpha equals a over r, and sine of alpha equals b over r. Let's look at an example utilizing the auxiliary angle formula. Here we are asked to write the square root of 3 times sine x minus cos x in the form r times sine of x plus alpha. So in this case, a is the square root of 3 and b is negative 1. Using the formula, it follows that r is 2. To find alpha, first we have that cos of alpha equals the square root of 3 over 2. So alpha is either pi over 6 or negative pi over 6. We also have that sine of alpha equals negative 1/2. So alpha is either negative pi on 6 or negative 5 pi on 6. Combining these two results, alpha can only be negative pi on 6. So altogether, we have that the expression can be written as 2 times sine of x minus pi on 6. To wrap up this section on trigonometry, let's look at a real-life modeling example that uses trigonometric functions. The forewings of a locust in flight move in a manner described by this formula, where theta represents the angle in radians that each wing makes from the vertical, and t represents the amount of time elapsed in seconds. There are many properties of the model that we can deduce from the given function. The period of motion, that is, the amount of time between wing flaps, can be found using the formula 2 pi over n, where n is the coefficient of t. Here we find that the period is about 0.059 seconds. The frequency of motion, that is, the amount of wing flaps per second, is found by taking the reciprocal of the period. Here we find there are 17 cycles, or flaps, per second. The amplitude of motion, that is, the furthest the wings stray from resting position, is simply the coefficient of the sine function. Here we find that it is 0.6 radians, or about 34 degrees and 23 minutes. We can also find information about the greatest possible wing angle by using our knowledge of the sine function. Since the range of sine is between -1 and 1, we know that the wing angle is maximized whenever the sine term in the given function equals 1. So the largest possible angle theta occurs when the sine term is replaced by 1, yielding pi on 2 plus 0.6 radians, or about 124 degrees and 23 minutes. The first time this greatest angle is achieved occurs the first time the sine function equals 1 for positive arguments, that is, when its argument is pi on 2. Equating these two arguments yields a time of about 2/100ths of a second. In summary, we have encountered several new trigonometric identities, including the compound angle formulae and double angle formulae, as well as the auxiliary angle formula. We have also seen, by example, how to interpret a trigonometric modeling function.